Hello everybody and welcome to another Teach Astronomy Twitch stream. How's everyone doing today? I hope everyone's, if you celebrated, everyone's Thanksgiving was lovely. And if you didn't celebrate, I hope your weekend was lovely, because weekends are cool too. Hi Salvasuria, how you doing? So today, because it is Monday, we are back with another book stream. Totally just realized I did not update the title, did I? I've been a little scatterbrained this morning. Let me do that real quick so new people know what we're doing. Chapter 3. Sorry about that. There we go. Update information. Okay. Hopefully that didn't confuse too many people, but I guess we shall see. So, like I was saying, another book stream. We are on chapter 3. Last week we did 2, and sequential order. But if you weren't here for the last couple of weeks, this is a book called Einstein's Monsters. There she is. And it's about black holes, the history of the discovery of them, the science behind them, all that stuff, in a more easily digestible format than, a physics paper or something. And it's written by my boss and the person who a lot of you have found this channel through, Professor Prof Impey at the University of Arizona. So we've been reading the first couple chapters once a week, and I'm actually going to be moving those files. Well, thank you, Jan. I tried something new with my makeup today, so but we're going to be moving the files and the videos from the past streams that we've done for the book streams onto our Teach Astronomy YouTube channel. So those will be archived forever. We were just trying to figure out if it would work better on that one or on the Astronomy State of the Art, where Professor Impey does all of his Q&As that we're slowly transitioning over to Twitch. But I think I'll be putting those on Teach Astronomy. So if you missed the first couple chapters, no worries. There's it's written in order, but it's not like a novel where if you miss the first part, you're going to be really confused. So feel free to hang out, even if you haven't seen the first couple. And you can go watch those later once I get those up. They'll probably be up by the end of the day because it's just going to take some time downloading and then re-uploading and all that jazz. But yeah. So I guess if we're ready, I'll just jump on into it. I feel like there was another housekeeping thing I had to say, but I can't remember. Also, I know last time we were having a problem with my microphone. I think I fixed it. I think it should be louder now. If you weren't here and you don't know what I'm talking about, it was just very quiet. So if you notice that I'm really quiet, let me know. I can switch to something different. Might take a minute, but if it's bothering you guys, I would rather switch over. So let me know. So we are going to be starting. I really need to get a bookmark for this book. I have a million, but I just decide every time, oh, I don't need a bookmark. It's fine. Okay. Here we go. So chapter 3 is supermassive black holes. Very exciting. All right. Is a dead star the only possible type of black hole? The requirement for a black hole is density high enough to generate such strong gravity that no light can escape. In principle, this could occur in larger and smaller objects than a collapsed star. Nevertheless, it was a surprise when supermassive black holes were discovered. Some so massive that they exceed the sum of all the stellar black holes in our galaxy. It was an even greater surprise to learn that one exists at the center of every galaxy. The section is the only radio astronomer in the world. The summer of 1937 was hot and humid in Wheaton, Illinois. 26-year-old Grote Reber was out in the vacant lot next to his mother's home every day, cutting wood and shaping metal from 7 in the morning until darkness fell. He was building a radio telescope. The dish was 10 meters in diameter, the biggest he could construct with available materials. When completed, it was by far the largest radio telescope on Earth, a precursor of modern versions that range up to 100 meters in diameter. For a decade, Reber was the only radio astronomer in the world. That's cool, being a pioneer, the whole field. And we also have a picture of that I can show you guys. Here it is. These pictures, if you don't have a physical copy of the book, these pictures are also in the book, but I put them in a PowerPoint so it's easier for you guys to see. So this says, the first parabolic radio telescope in the world, built by amateur radio astronomer Grote Reber in 1937. The first radio telescope was Kark-Jansky's dipole array. The 9-meter dish was built in Reber's backyard in Wheaton, Illinois. It is the prototype for all the future dishes in the young field of radio astronomy. It's very cool. I love that there's just like a big old platform next to it. But could you imagine, like, before radio astronomy is a thing, your neighbors walk by and see you building this, and they're like, "You gonna be transmitting some television?" Well, actually, TV wasn't even around, so it's like, what are you doing there? You making a really high-powered radio station or something? That would have been crazy. Okay, So for a decade, Reber was the only radio astronomer in the world. But he wasn't the first. Carl Jansky was trained in physics and was just 23 when he was hired by Bell Labs in Holmdel, New Jersey. I'm from New Jersey. It's so exciting. I know where Holmdel is. The company wanted to investigate the possibility of using radio waves 10 to 20 meters long for transatlantic telephone service. Jansky's job was to look into sources of static that might interfere with voice communications. In 1930, he built an antenna in a fallow potato field near the lab. The contraption looked like the wing frame of an early biplane, and it pivoted on a circular track on 4 rubber-tired wheels from a Model T Ford. By rotating the antenna, Jansky could tell the direction of incoming radio waves, while the radio signals were amplified and recorded by a pen on a moving paper chart in a nearby shack. Mostly, he detected static from nearby thunderstorms, but there was also a faint radio hiss. Within a year, Jansky had shown that the hiss was not of terrestrial origin. It kept the time of the stars, rising and falling not every 24 hours, but every 23 hours and 56 minutes. The radiation was strongest towards the center of the Milky Way, in the constellation of Sagittarius. Jansky's revelation caused a stir, and was reported by the New York Times on May 5th, 1933. This was the birth of a new way of studying the universe. For thousands of years of naked-eye astronomy, and hundreds of years since Galileo's first use of the telescope, all information from space had come from a slender range of optical wavelengths, a factor of only 2 from the reddest red to the bluest blue the eye can see. Now, humans had recorded signals from an entirely new region of the electromagnetic spectrum. Jansky proposed building a 30-meter radio dish so we could follow up his discovery. Bell Labs wasn't interested. They assigned Jansky to another project, and he did no more radio astronomy. That is not the end of this section, but I did want to mention, if you're interested in more information about Carl Jansky, we talk about him a little bit in a video that we did for Active Galactic. If you don't know what Active Galactic is, it's another YouTube channel. We have many, where we make short YouTube videos all about different stuff in astronomy, and we did one at the Very Large Array, and we did a whole tour and history of it, and it's named the Carl G. Jansky Very Large Array because, in to honor him. So there's some other information about him and stuff too, if you want to watch that. But we will continue. Jansky's work sparked Reber's curiosity about the source of cosmic radio waves. In the early 1930s, he applied to work with Jansky at Bell Labs, but during the Great Depression, no one was hiring. It sounds familiar. So he taught himself how to build a telescope and a receiver. He enjoyed working alone. As he put it, quote, "There have been no self-appointed pontiffs looking over my shoulder giving bad advice," end quote. He settled into a rhythm. By day, he designed radio receivers at a factory in nearby Chicago. After supper, he grabbed 4 or 5 hours sleep, then from midnight until sunrise his dish tracked around the sky while he sat in his basement recording the radio signal at 1-minute intervals. Eventually, he improved his receiver and bought an automatic chart recorder so he wouldn't have to sit up all night. This enabled Reber to embark on the first survey of the radio sky. Ooh, sorry. I didn't have a coffee this morning. Pardon the yawn. All right. Reber was isolated. He had no peers to exchange ideas with, and he was working at unexplored wavelengths. Imagine being the first sculptor in the world. Other people are painting and drawing, but nobody else is creating artwork in 3 dimensions. With nobody else speaking your language, you'd be lonely. Engineers took little notice of Reber's work, which he published in a radio engineering journal, as Jansky had before him. Astronomers, meanwhile, were uninterested or skeptical. After Reber confirmed Jansky's detection of radio waves from the Milky Way in 1940, he submitted a paper on what he called cosmic static to the Astrophysical Journal. The editor, Otto Struve, sent the paper to several referees. Engineers didn't understand the astronomical implications. Astronomers were confused by the radio jargon. Nobody was willing to recommend his publication. Struve decided to publish it anyway. The only radio astronomer in the world continued his lonely work. Oh, Coderish64, of course, you're welcome. That's the whole point. It's a free audiobook. You can string it all together. We like to bring education and astronomy and stuff like that and tools to as many people as we can, so it's a fun way. Anyway. With meticulous care, Reber mapped the sky. He worked at successively shorter radio wavelengths, knowing they would yield more accurate locations for the radio emission. By working at several wavelengths, he could diagnose the physical process causing the radiation. In 1944, he wrote a paper that included the first ever map of the radio sky. The paper also demonstrated that the emission process of cosmic radio waves was non-thermal, thus different from radiation that comes from an object at a fixed temperature. His maps showed that the radiation was concentrated in the Milky Way, with 2 other peaks of emission, in Cassiopeia and Cygnus. The first would prove to be a supernova remnant 11,000 light-years away. The second, coincidentally not far from the prototypical black hole Cygnus X1, would eventually prove to be a galaxy with immensely powerful radio emission, 500 million light-years away. It would take some time for astronomers to understand the nature of this galaxy, dubbed Cygnus A, which is the strongest radio source in the sky. And we have a figure for that. Wait, that's the old one. Hold on. There it is. So this is a picture. This image was made with a radio interferometer called the Very Large Array. Hey, that's what we were talking about. So this is data taken from the VLA. So this bright spot in the center is now known to be a supermassive black hole in a galaxy 600 million light-years away. Jets, which are these, of high plasma energy, travel out of the core and create diffuse lobes of radio emission far beyond the galaxy. So this is the radio emission, right? And then there's like a little bit of radio emission as well from the black hole itself, but a lot of it is in these jets that are being expelled outward. Cool. All right. Its discovery established Reber as an iconoclast. As he once advised a young student, pick a field about which very little is known and specialize in it. But don't accept all current theories as absolute fact. If everyone else is looking down, look up or in a different direction. You may be surprised at what you will find. That's cool. And that's the end of that section. So I can take a little break. Also, if you're here and you're new, welcome, first of all. Or if you've been hanging out and like not interested in chatting, that's okay too. But if you are interested in chatting and you don't have yourself a Twitch login yet, you should get one. Because then you can chat in the little sidebar here and hang out and talk to, the other viewers and myself, and it's a good time, and it's free to make a login and stuff. And then you can follow us, and you also get notifications on when we go live for all of our stuff, as long as the notifications are actually working. Sometimes they are spotty. Coder64 says, I've been programming a physics simulator for simulating a Falcon 9 flight and landing. Oh, that's really cool. That's very cool. Is that just as a fun project, or is that part of a job, or? That's awesome. Yeah, if you wanna throw out a, call for fellow programmers, feel free to, I don't know what you would put. I guess people could whisper at you. I think that's what DMs are in Twitch. Or if you want to put like your Twitter handle or something, feel free. Selva said, any idea how those radio signals are made into images? So, I don't know the specific details of it. Again, disclaimer, because I didn't say it in the beginning. Out of our group, I'm the film and television and Twitch expert. I have some background in astronomy because I've taken some classes on it and I've been working with the astronomy group, but I am not any sort of astronomer, astrophysicist. So just bear with me while we learn together. But essentially, radio signals are, when they're observed by the VLA, it's similar to how, when you use the big telescopes that are, using optical light, it's the intensity of the signals. It's like it's not like it's taking a picture with optical light either, most of the time on the bigger telescopes. It's like collecting data and it's collecting signals. So, so the radio signals, when they come in, they're, it's just data, and then you have to go, and there are ways that, and like programs that astronomers use. There's a lot of coding in astronomy, actually. But there are programs that astronomers can use to, what's the word? It's converted into digital signals. It's, I forget what the word is. I can't think of it, but essentially, like, put that data together into something that like looks like something. Let's get a better explanation of this. How do radio signals get turned into photos? We covered a lot of stuff on convert, transform, something like that. But we covered a lot of how radio astronomy works in a video, again, another video, on Active Galactic. I don't know if we talked too much about the reduction. It's data reduction. That's what I was trying to think of. So it's like a data reduction sort of things, I believe, is what I'm trying to say. Oh, here we go from NRAO. So... Oh, that's fun. Okay, I'm going to share this with you guys because NRAO has a little thing where you can try it at home and make yourself your own radio image if you're interested. I hope that whole link is actually... Yeah, okay. For some reason, sometimes it looks like in the chat that like half the link is just like not a link anymore, but it works. I checked it. But here it says... So the radio waves are focused onto the antenna. That's why you have the dish and then the thing at the top of the dish. So it all focuses onto the top receiver. The receiver amplifies the waves and converts them into a signal that can be stored into a computer. And then astronomers use computers to turn this information into pictures. So lots of coding, lots of, turning bits and bytes into a picture. But cool stuff. I'm just checking the chat really quick before I go on to the next section to make sure that I didn't miss anything. Oh, Full Ass Bear, hello. Good morning from Seattle. I think it was all just chatting about trying to figure out what word I was saying. Yeah, digital pictures of bits and bytes too, yeah, I guess. But yeah, it's essentially just you get these radio waves, you collect the radio waves, you turn it into a picture. There's a much more complicated explanation, I'm sure, if you wanted the serious details. I'm Vicky, by the way. Hi. Vicky, Victoria, whatever you want to call me. Yeah, I'm sure there's a much more in-depth explanation that you could find somewhere if you look on NRAO and stuff. So, yeah, getting data is always the hard part. Especially with, we talked about this a little bit in our news streams when Michael and I do our news streams, but as the sky gets more crowded and the Earth gets more crowded with radio signals, is going to get harder and harder. But we can chat about that another time. Alright, so the next section is galaxies with bright nuclei. Science doesn't flow like a river. Rarely are scientists carried smoothly along to the sea of understanding. More often, they're explorers traversing difficult terrain, sometimes in daylight and with steady progress, sometimes in a fog with no compass. There are detours and dead ends. Different people working towards the same goal don't always communicate or even know of one another's existence. It's rare that someone is smart enough or lucky enough to find high ground and see the larger landscape. At the turn of the 20th century, there was a fierce debate in astronomy over the nature of nebulae, the fuzzy patches of light that have been catalogued by William Herschel, and others, over 100 years earlier. Since many had a spiral structure and they didn't sit close to the plane of the Milky Way, like most star-forming regions, astronomers started to take seriously the hypothesis that they were, quote, island universes, separate systems of stars at enormous distances from our galaxy. If so, their spectra would look like the sum of the light of many stars, with the same absorption lines seen in the sun and other stars. So many S's. In 1908, Edward Fath at Lick Observatory looked at a spectrum of the nebula NGC 1068 and was surprised to see not just absorption, but also 6 strong emission lines, features that could only be generated if the gas was heated by some source of extreme energy. At the time, the result was so puzzling that it was ignored, and it would be 2 decades before Edwin Hubble proved that NGC 1068 was in fact a galaxy. In the early 1940s, Carl Seyfert was a postdoc at the Mount Wilson Observatory in Southern California. Done a video on that too. With Edwin Hubble as his advisor, Seyfert used the 60-inch and 100-inch telescopes, the most powerful telescopes then available, for his research. When Seyfert gathered his data, Los Angeles had 1/3 the population and 1/10 of the city lights it does now. He also benefited from truly dark skies during the blackouts that were imposed after the attack at Pearl Harbor. He took spectra of the nuclei of bright galaxies and found 6 similar to NGC 1068, with bright emission lines indicative of an energetic process. He also noted that the emission lines were very broad. The width of an emission line indicates the range of motion of the gas. In a normal spiral galaxy, the maximum rotation speed is 200 to 300 kilometers per second. Yet Seyfert was measuring Doppler widths of thousands of kilometers per second, suggesting that gas near the center of these galaxies was moving 10 or 20 times faster than anything previously measured. Material moving at this speed would fly away from the galaxy unless some great mass near the center was pinning it. Seyfert had a puzzle to solve. What could cause rapid motion of gas in the center of the galaxy? At the time, nobody knew. Like Rote-Reber's paper on cosmic static the following year, Seyfert's paper caused hardly a ripple in the astronomy world. It wasn't referenced for 16 years after its publication. The class of galaxies that was eventually named after Seyfert waited in limbo. Meanwhile, the new insights came from technical advances in radio astronomy. That's that section. I'm just looking at chat real quick. I'm so sorry if you can hear me drinking. I'll have to put the mic up next time. I see that you were talking about more coding stuff. Yeah, a lot of that is over my head. I've been looking into trying to start learning how to code, more for coding video games than for doing any sort of like data science stuff, because I really like video games. That's why I pushed us to go on Twitch. But start with C. Yeah, that was the plan. I was going to try to start with C, get a basis there, and then move to C++. Because it seems like a lot of the like Unity and things like that, the basis is in C and C++. So, Coder said you asked what this project was part of. So you're making a general is as general purpose as possible, so it can be used by any programmer to create their own modified versions of it, and also a GUI which would allow non-programmers to create physical bodies and simulate their phenomena. That's really cool. That's awesome. Oh, C# for basic dev with Unity? Yeah. All the C's, you know? Just learn all of them. I'll get my basis in C first, but that sounds really interesting. I like that. Yeah. Very cool. Thank you for sharing. C family is the beast, yes. Yeah, I think for for video game programming and a lot of programming, C is great. I've heard some people in the sciences, at least like people that I've talked to, some of them use Python. I've heard Python's a popular one. I don't know if a lot of people use Java anymore. Java's just Java. But, yeah. Anyway, for those who are not here for programming chit-chat, we can do that another time. But I'll keep going in this. So next section is Radio Astronomy Comes of Age. The pure sciences seemed irrelevant in the 1940s with the war on. However, many radio astronomers played a crucial role in the development of radar, which in turn was pivotal in the outcome of World War II. Battles were won by the first side to spot enemy airplanes, ships, or submarines. British and American engineers and scientists developed radar that could see for hundreds of miles, even at night. Radar helped to sink German U-boats. It allowed the British to spot incoming bombers, and it provided cover for the D-Day landings. It is often said that the atomic bomb ended the war, but radar won it. Radar also led to astronomical discoveries. In 1942, Stanley Hay of the Army Operational Research Group was puzzling over severe interference in England's coastal radar defenses. He realized that the interference wasn't coming from the enemy, but from the sun. Later in the war, he discovered the ionized trails of meteors while trying to track German V-2 rockets. Neither discovery could be published until the war was over. His group also confirmed the existence and the strength of the puzzling radio source Cygnus A. After the war, Hay continued military work at the Royal Radar Establishment in southern England, while others who worked on wartime radar became the pioneers of radio astronomy. Martin Ryle started the Cavendish Laboratory at Cambridge University, and Bernard Lovell started Jodrell Bank as a field station of the University of Manchester. Australia became a radio astronomy power due to the technical expertise it contributed to the Allied war effort. One of the world's best wartime radar labs was located in Sydney, and after the war, the lab stayed intact, with the staff switching to the study of cosmic radio noise. It's also quotes, noise. Noteworthy among them was Ruby Payne Scott, one of the best physicists Australia has ever produced, and the world's first female radio astronomer. After contributing to the war effort, she was the first to study solar radio bursts, and she developed the mathematical formalism for the type of interferometry used at radio arrays all around the world. She battled sexism her entire career, of course, and had to conceal her marriage since at the time married women were not allowed to hold full-time jobs as civil servants. God, don't get me started about how there should be more ladies talked about for what they did in science. But anyway. Meanwhile, European astronomy was kick-started at war's end by the redeployment of 7.5 meter antennas from German radar facilities to national observatories in Britain, the Netherlands, France, Sweden, and Czechoslovakia. This is a gratifying story of swords being turned into scientific plowshares. In 1946, Stanley Hay and his colleagues used their modified anti-aircraft radar antenna to show that Cygnus A varied in strength from minute to minute. Since light can only travel a certain distance in such a small amount of time, any variation timescale sets a size scale for a source of radiation. Fast variations can only be seen in very small sources of radiation. In this case, the object was determined to be very small, the size of a star. Martin Ryle suggested that Cygnus A might be a new kind of star that was bright at radio wavelengths but invisible at optical wavelengths. A radio star. This confused everyone. Stars like the sun emit feeble amounts of radio waves, so how could a star be such a bright radio source? As the radio astronomer J.D. Davies commented, there appeared to be an optical universe and a radio universe, which were utterly different, yet which coexisted. So there was obviously a need to tie them together somehow. The obstacle to progress in radio astronomy was angular resolution, the smallest angle any telescope can distinguish. Better angular resolution corresponds to a smaller angle. If light sources are closer together than the angular resolution of a telescope, they blur together. Angular resolution also affects the depth of vision. When sources blur into one another, it's impossible to tell which is nearer and which is farther. Imagine being myopic in a large room full of people. You may make out the nearest few faces, but all the rest are hopelessly blurred. It would be difficult even to count the people in the room. Put on glasses, and everything snaps into focus. Sharper images required either shorter waves or a brighter telescope. Angular resolution is proportional to the wavelength of observation, and inversely proportional to the telescope's size. Radio waves are millions of times longer than light waves, so radio astronomers start out at a serious disadvantage in comparison to their optical counterparts. They compensate for that in part by building big telescopes. Grote-Reber's dish was 9.4 meters in diameter, larger than any optical telescope at the time. Its sharpest images were 15 degrees across. That's the width of a fist, held at arm's length. There are many optical objects in a patch of sky that big, so it was impossible for Reber to deduce the source of the radio waves. Shifting to higher frequencies, which means shorter wavelengths, so 200 centimeters rather than 2 meters, a factor of 10 could be gained. To put this in perspective, visible light waves are 3 million times smaller than the 2-meter-long waves Reber observed. An optical telescope the same diameter as Reber's would make images 3 million times sharper. To produce an image as sharp as a 1-meter optical telescope would require a radio telescope the size of the United States. That's very large. The invention of interferometry solved the problem. In an interferometer, incoming waves from 2 or more radio telescopes are combined with the phase information of the waves preserved, meaning the exact timing of arrival of the peaks and troughs. Thus, angular resolution is given by the separation of the telescopes, rather than by size, so that 2 10-meter dishes separated by 1 kilometer have 100 times better angular resolution than either dish used separately. This technique is also called aperture synthesis, because it synthesizes a telescope with the resolving power of a very much larger telescope. So essentially that, to explain that, it's like, so the VLA is 27 operating, 28 total dishes that are spread out into a Y. And so instead of using just one of those telescopes to look at something, they use all 27, and then they're able to, because they're separated and they can separate them really far apart, it'll give them a lot better resolution, essentially. And then they'll be able to tell if things are like one object or if it's like multiple objects that are very close together, stuff like that. Anyway. In 1950, Graham Smith at the Cambridge's Cavendish Laboratory used 2 repurposed German antennas to measure the position of the bright radio source Cygnus A with an accuracy of 1 arc minute, or 1/30th of the moon's diameter, a hugely important breakthrough. And there's a... Here we go. There's... Is this the figure? Yes, it is. Okay. So we have a figure So this is fun. Okay. So this is a logarithmic plot of telescope size versus angular resolution, or the ability to resolve small features in an astronomical object. So like I was saying, the ability to see multiple objects within, like to be able to tell if one object is if multiple objects are blurring into one, or if it actually is just one object. Also, hello, welcome, Intro Fortis. Welcome to the stream. Glad you found us. We're reading a book actually right now. So if you want to hang out, feel free. We're reading. I'm going to switch back to me, so you're just not talking at it. I'm not looking at a graph. But we're reading a book called Einstein's Monsters by Professor Prof Impey. So hang out. We're having a good time. It's all about black holes. I'm going to switch back to that, by the way. There we go. But yeah, we do a bunch of stuff on this channel all about astronomy, because astronomy's cool. But yeah, so back to the graph. So for reference, the angular size of the moon is 1,800 arc seconds. So the dot at 10 millimeter and 20 arc seconds is the unaided eye. Where's that? 10 millimeters, 20 arc seconds. Oh, here it is. So this is, this represents the unaided eye, and the dot at an aperture of 2.4 meters and a resolution of 0.1 here is the Hubble Space Telescope. So the wavelengths of electromagnetic radiation are shown as diagonal lines, increasing from X-rays at the lower left to radio waves at the upper right. The largest single telescopes are about 10 meters at optical wavelengths and about 300 meters at radio wavelengths. Interferometers simulate a very large telescope, so give a very high angular resolution. So it's a little confusing because there's a lot going on. So it's showing where, like, how much, what's the word? What the angular resolution on these telescopes is, based on how big they are, and like what you can see with them. It's a little confusing. There are a lot of lines. Essentially, it's all just saying that the bigger the telescope, the more you can see. Yeah. Also, since we have a natural pause here, I'm just going to check the chat. Oh, just talking about some Python stuff. Yeah. Is that resolution using parallax? I'm sure there's some parallax used. Like, 'cause you have to take that, like, Is that resolution using parallax? How do you mean? 'Cause, like, so parallax, if I remember correctly, is the whole, if you have one point, or like if you're looking at something, you can determine how far away it is using parallax. I think. We're learning together, folks. Oh, no, my bad. It's the effect whereby the position or direction. Oh, okay, good. Gotcha. I misunderstood. Or, well, I guess parallax is used to determine where objects are. But parallax is essentially if you have two distinct viewers at different places and you're looking at the same object, it's the idea that they differ, which is how you can determine the distance. Is parallax used in this? I mean, probably. I think so. It's a little, it's a little different for radio astronomy. I'm sure they use it in some way. But at least the way that, like, I've understood it, it's like looking at things, right? So it's easier to understand, like, oh, of course they would with optical things, but yeah, if they're using, Coders is right. If they're talking about looking at something from different telescopes, it's that idea of, I think, parallax plus the what we talked about before with the determination of where the troughs and the top and bottom of wavelengths essentially helps you determine where objects are in the sky. I hope that all makes sense. Oh, somebody's writing. I still need to make us fun things that, do the fun notifications when things happen. But thank you so much, Virtual Assistant, for rating with a party of 3. Welcome. So if you have just joined us from Virtual Assistant, we are reading Einstein's Monsters. It is a book all about black holes, and we're just talking about black hole stuff. If that's something that you're interested in, please throw us a follow and hang out. And we're just talking about specifically like radio astronomy in this section. So that's how they increase the total aperture. Yeah, so the more telescopes and the farther apart they can put them, the farther they can look, essentially. So Adam Altogether recommended us. Oh, thank you. Yeah, I'm glad you enjoy it. But yeah, so it's essentially like when you have like something like the VLA or even bigger ones, the VLBA, it's a very large baseline array, I'm pretty sure, is a collection of radio telescopes that span like a huge chunk of the globe, and you can essentially like turn half the planet into a radio telescope that is just massive. So you can get really accurate. What's the word? You can really get a more accurate angular resolution and stuff. So you can really tell if like we were saying, like you can tell where an object is, if there are multiple there that are blurring together, stuff like that. It's very cool. Radio astronomy is really cool. All right, so back to reading. Where was I? There we go. So, the precise measurement of the position of Cygnus A got the attention of Caltech astronomer Walter Bade. Bade? If you guys know how to correctly pronounce Walter Bade, feel free to correct me, because it's got 2 A's. I don't know if that's different, but we're going to go with Bade for now. Within 2 weeks of receiving the data from Smith, Bade was in the observing cage of the 200-inch telescope on Mount Palomar, the most powerful optical telescope in the world. The German-born astronomer hadn't been allowed to enlist during World War II, so like Carl Seyfert, he used the wartime blackouts of Los Angeles to take photographs of unprecedented depth of the night sky. A vignette from a later interview paints a vivid picture. When he, quote, "When he told what he had seen and discovered in careful scanning of thousands of plates, the incredible grandeur of the cosmic realm, the galactic and extragalactic world, began to unfold behind numbers, pictures, and astronomical gossip. This man in his dark blue tie and gray suit, wearing brown shoes of enormous size, was absolutely fascinated by his research. Gesticulating, incessantly smoking, with carefully parted thin white hair, white somewhat bushy eyebrows, protruding hawk nose, Bade saw the mysteries of the universe as the greatest of all detective stories, in which he was one of the principal sleuths." End quote. When Bade pointed the 200-inch telescope, nicknamed the Big Eye, at Cygnus A, the resulting photographic plates thrilled him. "I knew something," this in quotes, sorry. Quote, "I knew something was unusual the moment I examined the negatives. There were galaxies all over the plate, more than 200 of them, and the brightest was at the center. It showed signs of tidal distortion, gravitational pull between the 2 nuclei. I had never seen anything like it before. It was so much on my mind that while I was driving home for supper, I had to stop the car and think. And thought he was going to say what he was thinking about. With cooperation of radio and optical astronomers, one important question had been answered. Cygnus A was a distant, distorted galaxy. Its spectral lines were redshifted by 5.6%, indicating that it was receding at 35 million miles per hour. In terms of an expanding universe model where redshift indicates distance, that meant it was 750 million light-years away. The radio waves we see now were emitted when life forms on Earth were no larger than the head of a pin. Bade had been thinking of the power that might result from cosmic, quote, train wrecks, and proposed that super bright Cygnus A comprised a pair of colliding galaxies. Rudolf Minkowski, one of Bade's colleagues at Caltech, questioned his theory, and Bade tried to bet him $1,000 that his hypothesis would prove correct. Black hole theorists evidently aren't the only scientists prone to gambling. If you're new here, that's a reference to the fact that Stephen Hawking and his colleagues enjoyed betting each other on, black hole discoveries in the earlier stages of their research. At the time, that was a month's salary, that $1,000. Minkowski wouldn't bite, so Bade lowered the bet to a bottle of whiskey. Minkowski conceded the bet after he took a spectrum that showed emission lines from very hot gas near the center of Cygnus A. When two galaxies collide, the gas they contain heats up. Bade later griped that Minkowski paid... I'm so sorry. I just got so spooked. I thought I saw something move in the corner of my room. So sorry. Oh, that's so cute. I love the little hearts. I'm sorry. I'm going to continue now. Virtual assistant is chat script based? What? Somebody explain to me what that means while I keep reading. I'm going to continue now. I've been thoroughly startled. Anyway. When two galaxies collide, the gas they contain heats up. Bade later griped that Minkowski paid off the bet with a flask of whiskey rather than a bottle, and then drained the flask on a subsequent visit to Bade's office. Nonetheless, a number of theorists later decided, through careful calculations, that a collision couldn't explain the radial brightness. A central question remained unanswered. How could Cygnus A emit 10 million times more radio waves than the Milky Way? Averted Vision. Okay, that's the end of that section. I don't know what just happened, but yeah, out of the corner of my eye, I saw it probably was just the light moving because some of the light's coming through and hitting some stuff in the corner. Bird probably flew in front of it or something, but I swear to God, I was like, is there a small creature in here with me? Anyway. Telescopes do use parallax, yes. Anyway. I guess we shall continue. I wonder how long this chapter is. What time is it? 10:55? We've been going for about an hour. Oh, this is a long one. Okay, not too bad, not too bad. I've got water this time, so... that's good, because last time I was like, oh, coffee's enough. Don't do that. If anybody has good suggestions for teas or home remedies to drink after talking for a solid 2 hours, let me know, because my throat gets a little scratchy after these. It's worth it, though. This is really fun. I enjoy this. Okay. So next section is a Dutch astronomer discovers quasars. In 1950, a new mechanism was proposed for cosmic radio waves. When electrons move at close to the speed of light in a magnetic field, they travel in a spiral pattern and emit intense radiation over a broad range of wavelengths. This is called synchrotron radiation. Synchrotron radiation was created in lab accelerators in the 1940s. But it was a surprise to learn that this process could occur when particles are accelerated in regions of space hundreds or thousands of light years across. In 1958, at an international astrophysics conference in Paris, scientists presented papers arguing that synchrotron radiation could explain solar flares, afterglow from a 1054-80 supernova in the Crab Nebula, the peculiar elliptical galaxy M87, and possibly Cygnus A. When Cambridge radio astronomers published their third catalog in 1959, optical astronomers targeted the most compact radio sources, which offered the best chance of finding an optical counterpart. As before, Caltech astronomers were at the center of the action. Tom Matthews and Alan Sandage observed the 48th object in the catalog, 3C48, and found a faint blue object at the radio position, surrounded by wisps of nebulosity. The light varied rapidly. The object couldn't be much bigger than a star. Most puzzling of all was the spectrum. It had strong and broad emission lines that couldn't be identified with any known element. Matthews showed it to Jesse Greenstein down the hall. But Greenstein, an expert on stars, had never seen a stellar spectrum like it. Unable to explain the data, Greenstein put the spectrum in a drawer and forgot about it. Lots of forgetting about things, or ignoring things, in radio astronomy, and science in general. It takes time to figure out what things mean, right? It fell to Martin Schmidt to take the next step. The young Dutch astronomer came to Caltech to work on star formation in galaxies, but he was intrigued by the puzzle of radio sources. In 1963, radio astronomers in Australia took advantage of the moon eclipsing the 273rd object in the 3C catalog to measure a very accurate position for the source. Schmidt went to the 200-inch telescope and saw a blue star-like object with a linear feature off to one side. A spectrum of the object showed mysterious emission lines like those seen for 3C48. When Schmidt attempted to match the pattern of lines with a well-known element, he realized the features were hydrogen lines, shifted 16% to the red. Taking redshift as due to cosmic expansion, 3C273 was moving away from us at the incredible speed of 100 million miles per hour. 4 classic papers describing Schmidt's discovery were published in the journal Nature. 50 years later, he recalled the moment of discovery, interpreting it as a cosmological redshift, which I soon I'm going to start that sentence over. Interpreting it as a cosmological redshift, which I soon did because it was so bright in the sky. The luminosity turned out to be very high. And that was remarkable, because it was immensely brighter than normal galaxies, even the biggest galaxies. So here you have something that is out in the universe, more luminous than an entire galaxy, and it looks like a star. It was an astounding experience. And we have a figure. It's figure time. Boop. No, that's the old one. Hold on. There it is. So, this is, let me pull up the description. This is Martin Schmidt and Palomar. So on the left is the Palomar 200-inch telescope and the image of the quasar 3C273. So that's not just like something weird going on in the sky. That's the image, and that's the telescope. And then this is Martin Schmidt. And then on the right, this is the spectrum here of 3C273. So you can see the different emission lines marked. I'm so sorry, I realized I did that like pop noise, and I hope that wasn't like super loud for you guys. Sometimes I forget that I'm talking into a microphone. But yeah, so this is the spectrum with the emission lines, and then this is a piece of, well, this is the title page of the paper that announced the discovery, and it looks like it was published in the journal Nature. Very cool. Very fun. All right. So with the help of Schmidt's insight, Greenstein dug up the previous spectrum of 3C48 and quickly identified lines from normal elements redshifted more than twice as much, by 37%. 3C273 was 2 billion light-years away, and 3C48 was 4.5 billion light-years away. Light from the latter was emitted just as the Earth was forming and had been traveling through space ever since. Both objects were emitting 100 times the light of an entire galaxy, yet were smaller than the solar system. Martin Schmidt coined a new term for this extraordinary class of objects. Quasi-Stellar Radio Source, or quasar. Yeah, quasars are cool. I like quasars. Okay. Since the pivotal work was done in Los Angeles, Pasadena having been subsumed by the sprawl of Los Angeles long ago, let's use the greater Los Angeles metropolis as an analogy. Hey, that's where I live. Imagine you're hovering high above Los Angeles at night in a helicopter. In the city of roughly 10 million, there are approximately 10 house, street, and car lights for every person, for a total of about 100 million lights. I'm rounding these numbers to the nearest order of magnitude for simplicity's sake. If Los Angeles were a galaxy, each light would represent about 1,000 stars. Now imagine that in downtown Los Angeles, there's a single point source of light that shines several hundred times brighter than the entire city, yet it's only a few inches in size, no bigger than any of the individual lights. If we could rise high above the Earth so that the city was thousands of miles below us, the intense central light source would remain visible long after the individual lights had faded from view. From a great distance across the universe, a galaxy can be too small and faint to see, but its bright core shines brilliantly. That's a quasar. Cool. And that's the end of that section. And really quick, I'm just going to check some Twitch things. Doing good. I hope everybody's having a good time. I know there's there's only so much that we can chit chat about because we're reading. How can a black hole have inescapable gravity? That's a good question. Well, it's because it does, really. I mean, so the whole thing behind a black hole is that it has inescapable gravity because the star that it used to be, and there was a little bit of discussion in this in chapter 1, but the star that it used to be, so stars, explode, collapse, towards the end of their life, turn into either a white dwarf, a neutron star, or a black hole based on how large they are. And the thing is, when they collapse in on themselves, it's this huge amount of gas and dust and all this stuff, and matter condensing so small that it's so dense that it creates this incredibly intense gravity, so no light can escape. It's crazy and wild because the gravity is essentially stronger than the speed of light in a way. And yeah, it's, like Salvasoria said, it's because of density. It's because you squish all of that mass down, it becomes so dense that it just sucks everything in. Yeah. Alrighty. So, next section. Astronomers harvest distant points of light. The most striking property of quasars is their high redshift, indicating large distances and high luminosities. The expansion of the universe stretches the wavelengths of photons that travel through it, and that effect is called the cosmological redshift. Redshift, written Z, is defined as, this is an equation, so it's not going to make a super amount of sense. I'm going to type it in the chat, because I feel like that's easier to look at an equation like that. So it's 1 plus Z equals, I hope Twitch doesn't do something really weird with this, because it's an equation. 1 plus Z equals R little o over R little e. So that O and that E are like what's the word? It's not above the letter, it's below the letter. The little letter. But Student McLeod said any object with mass has an escape velocity. The escape velocity of a black hole is greater than the speed of light. Yeah, that's what it is. Subscript, thank you. So the O and the E are in subscript, and I will explain what all that means. So I just wanted you to be able to see it. So redshift, written Z, is defined as 1 plus Z equals RO, subscript O, divided by R subscript E, where I'm going to just say RO. It's a lot. Where RO is the size of the universe, or the distance between any 2 points in space, when the light from an object is observed. And RE was the size of the universe, or distance between any 2 points in space, because all space expands at the same rate, when the same light was emitted. So, to say that again, so that equation is, so it's 1 plus redshift equals the size of the universe when the light from an object is observed, divided by the size of the universe when that same light was emitted. So, since the universe is expanding, the light from the object being observed is going to be a lot larger than the light from the object. Or the size of the universe when the light, observed wavelength divided by emitted wavelength. No, I think the R's are just the size of the universe. The wavelength stuff is so it's literally just like, so the first, like, RO is the, when it's observed, how big's the universe. So to simplify it, say if the universe is 10 big, or whatever, when you see it, right, when you observe this thing. But when the light was emitted, so based on, how far away it is, how long it takes to get to us, you can determine how long ago the light was emitted. Say when it was emitted, the universe was 7 big, just trying to simplify it. It'd be 10 divided by 7. Does that make sense? I think. I hope. Let me know if it doesn't, and I can describe it again. Quantum entanglement moves faster than light. I believe so. I think quantum mechanics gets weird. This is a little off topic, but let me look. Also, for the new people here, another little disclaimer. I am, in our TeachAstronomy group, I am the Twitch and film and TV expert, and secondarily, I know my stuff about astronomy because of some college classes and my work with Professor Impey and the rest of the team, but I will not claim to be an astronomer or an astrophysicist, so I am learning with you. I do know some, I guess I would know a little bit more than the average person just because I've been working with this group for a long time. But, let's see, is quantum entanglement faster than light? Salvasurgia said it is. I'm pretty sure it is. Yeah. And that's why quantum physics is very weird. Is it correct to use text underscores for subscripts? I think it's possible. I actually don't know how it's typically written when you can't actually do the subscript. I don't have a lot of experience writing with subscript, I guess. I did it back in, like, physics and chemistry and stuff, but you work with, like, Microsoft Word, and there's, like, an option for that. I'm not sure what the official way to do it is. Anyway, where were we? We were at the equation. That's right. Okay. So explain the whole equation. So it says, and of course there's another one. Is it an astronomy joke? I'm gonna look this up really quick. Averted vision is a technique for viewing faint objects, which uses peripheral vision. Okay. I figured it was something like that. Yeah. That's very funny. The subject is discussed in the popular astronomy literature, but only a few rigorous studies have quantified the effect. Okay, so it's not like a super... That's cool. Yeah, you can even see that if you're like out looking at the night sky and you're trying to look at something but you can't quite see it. But if you like look a little bit to the side, it might actually be brighter. Yeah, that's a fun joke. I like that. Yeah. Yeah, quantum entanglement's interesting. Yeah, it's fun, like I'm again, I don't claim to be an expert, but I love learning about this stuff, and that's why I joined the group in the beginning, like 4 years ago, and why I'm still here. I will put it in the suggestion box, Student McLeod. It makes sense. Oh, Coursera doesn't let you do it either? See, that's weird, because like I understand if Twitch is like, well, who's going to use Subscript on a platform that is mostly for, gamers? And it's like, that's fair. But Coursera for sure should have that. I just lost my page. I just took my finger out of the page. Oh my gosh. I will put it in the suggestion box though. All right, I found it. Okay. There's going to be another equation, so get ready. I don't know what that Greek letter is. Does anybody know what this... I wonder if I can hold this up and it'll focus. There's a reason... No. There's a reason I took pictures of the figures, because that doesn't work. Looking up the Greek alphabet really quickly. Sorry, guys. Because they use one in here and I don't know how it's said. I used to know it. That was a long time ago. Goodness. I don't know. We're gonna call it upside down Y. It doesn't even allow you to copy them. That's very frustrating. Yeah, Coursera should do something about that, especially if it's an educational platform. Anyway, okay, we're gonna get back to this. So we're talking about the equation. It's exactly the same relationship for radiation. So 1 plus Z equals upside down Y under subscript O divided by upside down Y subscript E, where the first one is the stretched or reddening wavelength of a photon we observe now with a telescope, and the second one is the wavelength of that photon when it was originally emitted. Lambda! Sure, we're gonna go with lambda. If that's what it's like, I have paper in front of me. It looks like this. This is what you guys are all here for, right? Trying to help me figure out what Greek letters are. It looks like this. If this is lambda, we'll go with it. But yeah, it's that was all to say, it's the same relationship for radiation. No more, it looks like there's no more equations for a little bit, so we're going to continue. The farther away a galaxy is, the faster it's receding. In fact, every galaxy is moving away from every other galaxy. That observation, made by Edwin Hubble in 1929, led to the idea of an expanding universe. When redshift is small, it's roughly equal to the recession velocity as a fraction of the speed of light. Before quasars were discovered, the most distant object known was a galaxy in the Hydra cluster, at a redshift of Z equals 0.2. Within 2 years, Martin Schmidt has pushed the redshift record to Z equals 2.0, with 3C9, a quasar receding at 80% of the speed of light. It's really fast. The light we see now was emitted when the universe was a quarter of its current age. Since distant light is old light, astronomers use faraway objects as time machines. Quasars are probes of the distant and ancient universe. Finding quasars was hard work in those early days. Radio astronomers had to grind to get accurate positions. A typical day at the telescope would be made up of two 12-hour shifts, since radio waves can be equally well detected by day and by night. The maze of electrical connections in the control room had to be checked and double-checked. Plugs would connect the signals from different telescopes or parts of an array into a correlator, and only an expert could keep track of the spaghetti junction. These were the very early days of computing, so signals were recorded in an analog fashion on magnetic tape. It was a full-time job to monitor the tape decks and spool up new tapes, making sure the tapes never ran out. The signals were then fed into a mainframe computer on punch cards to monitor the changing strength of the radio signal as the source moved across the sky and combine it with accurate clock readings to calculate a position. Many days and many sweeps of the sky were needed to get a single accurate position. The life of an optical astronomer was slightly easier and more glamorous. They rode the prime focus cage of a large telescope, suspended above the primary mirror like a fly caught in a metal web. The open slit of the dome looked out onto the glittering star fields. They would take unexposed photographic plates into the cage, sealed in a light, tight box, and carefully transfer them to the camera where they could be exposed to the night sky. Then they would use buttons on a small paddle to make fine adjustments to the rate the telescope tracked across the sky, to ensure the images were as sharp as possible. There was glamour, but tedium too. In winter, there were cold, 12-hour-long nights, with not much to do but push guiding buttons every few seconds and change plates every few hours. Optical astronomers might have to spend a whole night at a telescope to measure the redshift of a single object. Single-coded, you did it. How'd you do it? Well, at least it's not subscript, it's the other one. Single-coded figured out something. Anyway. With just a few dozen quasars cataloged, astronomers noticed that quasars were bluer, that is, hotter, than any star. Several researchers realized that there were other equally blue quasi-stellar objects that weren't associated with any radio source. Spectra revealed that many of these blue objects had high redshifts. They were quasars too. Excited by this discovery, astronomers did photographic surveys over large swaths of the sky to harvest objects with the bluest colors. The method was highly effective. Quasars selected in this way outnumbered quasars with strong radio emission by a factor of 10. Occasionally, the competitiveness of the hunt for quasars spilled into acrimony. In 1965, Ellen Sandage at the Carnegie Institution wrote a paper about the new class of radio-quiet quasars, and such was his reputation that the editor of the Astrophysical Journal published the paper without peer review. Fritz Zwicky at Caltech was incensed, as he'd previously discovered compact galaxies with quasar properties. A few years later, he wrote in the Vituperative. That's a new word. That's fun. A few years later, he wrote in the Vituperative foreword to his book on the properties of peculiar galaxies, quote, "In spite of all these facts being known to him in 1964, Sandage attempted one of the most astounding feats of plagiarism by announcing the existence of a major new component of the universe, the Quasi-Stellar Galaxies. Sandage's earth-shaking discovery consisted of nothing more than renaming compact galaxies, calling them interlopers, and quasi-stellar galaxies, thus playing the interloper himself." End quote. So much for genteel academia. Competition between Carnegie and Caltech led to many ambitious projects that are driving optical astronomy in the 21st century. First, Caltech built the twin 10-meter Keck telescopes in Hawaii, while Carnegie built the twin 6.5-meter Magellan telescopes in Chile. Carnegie is now lead partner in the 22.5-meter Giant Magellan telescope, and Caltech is lead partner in the planned 30-meter telescope. Both are billion-dollar projects with international partners. As astronomers seek to harvest ever more distant points of light, their, quote, toys are getting more complicated and much more expensive. The University of Arizona is making the mirrors for the Giant Magellan telescope. Every year or so, I visit the facility under the football stadium where 20 tons of pure glass in small chunks are put into a tub 30 feet across, heated to 1170 degrees Celsius, and spun into a parabolic shape. When the huge mirror oven is spinning, with flashing lights and waves of heat pouring out, it's like a sinister fairground ride, and the engineers nearby, wearing white coats and safety goggles, look like mad scientists. 3 months later, when the mirror has fully cooled, it's polished to near perfection. It amazes me to think that if the finished mirror was expanded to the size of the continental United States, the largest undulations or blemishes would be under an inch high. The Giant Magellan Telescope uses 7 large mirrors, with 6 of them arrayed like flower petals around the central element. Meanwhile, the 30-meter telescope will be constructed with 492 hexagonal mirrors, each 5 feet across. Both projects are racing to be the new largest telescope in the world. Each will spend a significant fraction of its time studying quasars. That's the end of that section. I'm really starting to feel it in my throat now. Superscript. Thank you. Anyone who wants to use a bunch of superscripts. Oh, you did both of them. Okay. If anybody wants to spam the chat with superscripts and subscripts, feel free now. Now we know. This wiki does sound like he was a cantankerous fellow. Yeah, not cool to just like take Oh. I mean, like, yeah, I guess I understand why he was upset, you know? But he's very angry about it. Alright, let me see how much more we have today. I love how in the beginning of when I started these readings every Monday, I was like, oh, maybe sometimes I'll do 2 chapters at a time, 3 chapters at a time. We'll see how it goes. And now I'm like barely getting through one in 2 hours. Because we're chatting and stuff. We're having a good time. So that's okay. Alright, we've got about like 12 pages left. So we shall continue. Hypothesizing massive black holes. Even before quasars were discovered, there were reasons to believe something very unusual was going on in the center of some galaxies. In 1959, a calculation showed that the broad emission lines in Seyfert galaxies could be explained... Oh, did my mic just do something weird? I thought I saw it, like, hold at red for a second, so apologies if it got really loud. Anyway. Where was I? In 1959, a calculation showed that the broad emission lines in Seyfert galaxies could be explained by gravity from a compact object 1 billion times more massive than the Sun. English theorist Geoff Burbidge succinctly stated the challenge of radio galaxies. The energy they contain in magnetic fields and relativistic particles requires the complete transformation of up to 100 million solar masses into energy. Relativistic particles are particles moving at close to the speed of light. Armenian theorist Victor Ambartsumian proposed, quote, a radical change in the conception of the nuclei of galaxies, saying, quote, we must reject the idea that the nuclei of galaxies are composed of stars alone. Hypotheses swirled. Perhaps the energy resulted from explosions in a dense star cluster, as one supernova set off others in a chain reaction. Perhaps a star cluster could evolve to very high densities by collisions ejecting large amounts of gas. Perhaps the energy came from a single supermassive star. Then, within a year of Schmidt's dramatic discovery, a pair of theorists suggested that the source of quasar power was accretion onto a supermassive black hole. They recognized that stellar fusion was too inefficient to generate quasar power. A gravitational engine is needed. With mass spiraling into the innermost stable orbit of a massive black hole, mass could be converted into particle and radiation energy with an efficiency close to 10%. Even at this efficiency, the most luminous quasars would require black holes 1 billion times the mass of the Sun to power them. The astrophysics community didn't immediately swoon for supermassive black holes. Remember that 1964 was the year in which the term, quote, black hole was coined, and Cygnus X1 was first detected. The idea of stellar mass black holes was still a novelty, yet here were theorists suggesting black holes 1 billion times more massive. It sounded like wild speculation. Can you imagine a factor of 1 billion? It's the difference between 1 grain of sand and a sandbox full. It's the difference between having enough money to buy a burger and being the richest person in the world. It's the difference between the mass of the people in your immediate family and the mass of Mount Everest. Even seasoned astrophysicists were taken aback by the thought of black holes as massive as small galaxies. The extreme energy requirements of quasars hinge on the fact that they are at large distances from the Earth, and thus must have very high luminosities to be as bright as they are. Luminosity is an intrinsic brightness, or how many photons the source emits every second. If quasars weren't at the distances indicated by their redshifts, then those energy requirements would be eased. The logic goes like this. A 100-watt light bulb at a distance of 100 meters would appear very faint. But if the light bulb was actually 100 kilometers away, it would have to be 1,000,000 times more luminous to appear to you to have the same brightness, making it a 100 megawatt light bulb. Quasars are faint, but so far away, billions of light years, that they must be fantastically luminous. This issue led to a small but vocal group of astronomers, including some highly respected names, to question the cosmological nature of quasar redshifts. The cosmological redshift in an expanding universe model translates into distance. These astronomers pointed to places where quasars were seen near galaxies at much lower redshift. There were more of these than should happen by chance. They noted an excess of specific redshifts that had no explanation in the cosmological interpretation. These statistical claims were not compelling to most astronomers, but arguments based in the physics of energy density were more troubling. Physicists argued that quasars would, quote, choke on their own radiation and be quenched before they could ever shine brightly. Quasars with very rapid radio variability were so compact that when relativistic electrons emitted radio photons, they would hit those photons and boost them to optical, then X-ray, then gamma-ray frequencies. The result would destroy the radio source and turn it into a gamma-ray source. In the mid-1960s, there were many heated debates on this topic at conferences with no consensus. It took new and better radio observations to make progress. That's the end of that section. I see 1964 in the chat. Is that one of the years I mentioned? Sometimes I forget what I read. 1964 was the year in which the term black hole was coined? Yeah. Is that just like 1964? Good year. Yeah, Cygnus X1 was also shown off to the public in 1964. When it was detected and stuff. Yeah, a good year for radio astronomy. Alright. Let's keep going. So mapping radio jets and lobes. Radio astronomers could be forgiven for feeling a little peeved. They provided the first evidence of extreme energies in galaxy nuclei and the accurate positions that allowed quasars to be discovered. But quasars can't be understood without measuring a redshift, which requires an optical spectrum, and most quasars turn out to have feeble radio emission. It seems like all the action was in optical astronomy. But radio astronomers had another trick up their sleeve. In the discovery phase of quasars, they had used dishes separated by hundreds of meters to get positional errors of about 1 arc minute. However, by increasing the separation in an interferometer to a kilometer and using as short a wavelength as possible, they reached accuracy of an arc second, close to the accuracy of an optical position. They could map the radio sky as accurately as optical astronomers. Seen in this detail, radio sources were amazingly diverse. There were radio galaxies where the optical counterpart was obviously a galaxy, and quasars where the optical counterpart was star-like. The most commonly seen type of radio source has huge lobes of radio emission straddling an elliptical galaxy with radio emission in its core. And in some cases, the lobes extend several million light-years into intergalactic space. The galaxy often has a peculiar or disturbed morphology. It looks like beams of high-energy particles are being ejected from the center of the galaxy and powering the radio glow in the double lobes. Cygnus A is a beautiful example. We've encountered galaxies with intriguing and unusual properties. Some have strong radio emission, others have strong X-ray emission. Some have intense optical emission and rapidly moving gas near their centers. None of this behavior is characteristic of a galaxy that's simply a large collection of stars. Astronomers use the term active galaxies to refer collectively to galaxies where the nuclear regions are particularly energetic. That's what active galactic is named after. Okay. Because I'm an optical astronomer, I generally prefer data I can see. But to understand active galaxies, I've used the Very Large Array in New Mexico, working in the same control room where Jodie Foster heard a message from aliens in the movie Contact. It's a great movie. The VLA is a set of 27 dishes, each 25 meters in diameter, that can be arranged in a Y-shaped configuration spanning 25 miles. The dishes move on railroad tracks to make the separations between dishes larger or smaller. Oh, gosh. Got a yawn there. It caught me by surprise. Oh, of course, Charlie. Thank you for being here. I remembered this time. I didn't call you I Like Bossa Nova. I called you Charlie. So the VLA is a set of 27 dishes. The dishes move on railroad tracks. Did I read that already? It took a while to get familiar with the jargon of radio astronomy. While the local radio astronomers readily helped me reduce my data, I noticed that they liked to retain an aura of mystique about their subject. I was at best an honorary member of the tribe. Radio astronomers focused particular attention on the sources that were unresolved by the existing interferometers, where variability indicated the source wasn't much bigger than our solar system. In the 1960s, they set about making a radio telescope as big as the Earth. They had to figure out a different way to combine the signals from different telescopes, since cable and microwave links wouldn't work on transcontinental scales. Their method was to record the signal from each telescope on magnetic tape, with the time recorded by an atomic clock, and then later bring the tapes together to create interference fringes and eventually a map. Data reduction was tedious and depended on advances in atomic clocks, computers, and magnetic tape recorders. In 1967, groups in the US and Canada observed several sources over a distance of 200 kilometers. Within a year, they added increasingly remote antennas in Puerto Rico, Sweden, and Australia. The baselines went up to 10,000 kilometers, or 80% of the Earth's diameter. Angular resolution improved by a factor of 1,000 to 1,000th of an arcsecond. The angular resolution of a dime on top of the Eiffel Tower as seen from New York City. And we have a figure, so let me finish the sentence. And radio astronomers could now produce images that were much sharper than those of optical astronomers. Ooh. Okay, let me get that figure up for you guys. Is that it? Yes, it is. Okay. Here we go. So this is the Very Long Baseline Interferometry, or VLBI, is the method by which signals from widely separated radio telescopes are combined to simulate the very high angular resolution of a telescope the size of the maximum separation between the telescopes. So, light arrives from a distant quasar at slightly different times at two telescopes, here and here, with a time delay that is determined by simple geometry, which is what's happening here. So they're figuring out the delay time, and the separate radio signals are combined by a piece of electronics called a correlator, which is right here. Correlators are usually massive, at least the one that I saw. There's a correlator room. I think when we went to VLA, it was either on site or it was at their offices in the city nearby, because there's a very small city called Socorro that is about 50 miles from where the VLA actually is, because VLA is just in the middle of nowhere. And I forget if the correlator was there in the office building, but it's got its own room. It's massive. It's crazy. And that's what combines the signals based on, the geometry of figuring out where everybody is. And then they can see things way clearer. All right. This new technique was called Very Long Baseline Interferometry, or VLBI. In 1970, radio astronomers studying quasars using VLBI noticed that the most compact radio sources had one-sided jets, and they were often blobs or hotspots within the jets. In data gathered over the course of a year, they could see the blobs moving away from the nucleus. Astronomers are used to the huge timescales of the extragalactic universe, where it takes a galaxy hundreds of millions of years to rotate once. So it was gratifying to see changes from year to year. But when they converted the apparent transverse motion of the blobs into a speed, they got a shock. The separation speeds were 5 to 10 times the speed of light. Was this a violation of relativity? No, it was an optical illusion. Because the jet in compact radio sources is pointing nearly at us, and the blobs are moving at close to the speed of light, they can appear to have very rapid transverse motion. It's like someone on Earth using a powerful light beam to sweep a spot of light across the moon's surface. If the beam pivots quickly enough, someone on the moon could see the spot appear to move faster than light, even though the photons in the light beam are traveling at light speed and no quicker. This phenomenon, called superluminal motion, has been seen in dozens of compact radio sources. Exquisite mapping of radio sources show that the radio astronomers can make images just as beautiful as images in optical astronomy. We have a figure. The data support... Sorry, I think there's a typo in the book. The data supports the hypothesis of supermassive black holes. Oh, I guess data can be plural. So the data supports the hypothesis of supermassive black holes. Strong radio emission implies that a particle accelerator is operating, and the compactness means the radiation comes from a tiny region of space. Only a gravity engine, such as a black hole, can do this. Also, since galaxies have angular momentum and a compact object at the center of a galaxy should be spinning, gas will escape along the poles of the spin axis. And we can look at this figure that shows this a little bit. So this is NGC 1052, and this is a sketch of the horizontal jets and a cross-section through the vertical accretion disk. This is the sketch. Oh, no. I'm sorry. This is the data. That's the sketch. So it says a magnetic field helps align and power the jets, and the data allows the field strength to be measured near the event horizon of the central black hole. So the black hole's in here, and these are the jets. And it looks like here, I think these might be the blobs they were talking about. Possibly. But yeah. Alright. A black hole can be a particle accelerator far more powerful than the best man-made machines. Gravity powers twin jets of magnetized plasma that shoot out from close to the black hole at nearly the speed of light, extending far beyond the edge of the galaxy to illuminate the radio night. Right, that's the end of that section. Alright. Oh, this is random, but on Wednesday this week we have our for anyone who's new here. On Wednesdays we do an astronomy news chat every other week, and the opposite weeks we do like just a chit chat about something in astronomy. And then Fridays we do an amateur astronomy stream. And if anyone has anything in the news that I should look at, that you guys would want to talk about on Wednesday, feel free to throw those in there. If not, I'm sure I'll find some stuff. But I would love to talk about things that you guys would be interested in. So, it's been a minute since we've done a news video, because Thanksgiving last week, and then before that I think we did the exoplanet video. We go live tomorrow at, I believe it should stay as what it is right now. I think on the schedule it says 1 o'clock Pacific. I'm pretty sure. It'll probably stay that way. My coworker Michael and I, we do those together, and he is still in his undergrad, so he still has classes and stuff sometimes, and I know it's like finals-y time, so Sometimes we do have to like move things around every once in a while, but I think tomorrow should be, not tomorrow, Wednesday, should be at 1 Pacific. So that would be in like, if you're not in the same time zone as me, it's 11:41 a.m. now, so like an hour and 20 minutes from now we would be starting. How about the lunar eclipse? Yeah, that's a good thing to talk about. About 8 hours difference? Okay, gotcha. Oh, and there's another Nature article. Very exciting. Let me click on that. Oh, that's spooky. So the Nature article that Single Coded just put in is titled "Hints of Twisted Light Offer Clues to Dark Energy's Nature." Yeah, I'll for sure. I'm not going to look at stuff too much right now. But feel free, throw some links in, throw some suggestions in if you've got stuff that you'd want us to talk about. And I'll be sure to look at those before we do Wednesday. All right. Next section is the Zoo of Active Galaxies. In the parable of the elephant and the blind men, each man touches an elephant to see what it's like. I'm going to show you the figure while I read this. If I can find it. There it is. This is the image that the parable is from. One feels a leg and says the elephant is like a pillar. Another feels the tail and says it's like a rope. A third touches an ear and says it's like a palm frond. And a fourth grasps a tusk and says it's like a pipe. The parable illustrates the dangers of inference, using incomplete information. With animals in mind, let's look at the Zoo of Active Galaxies. Active galaxies are defined by a negative. They show energetic behavior that can't be explained by stars or stellar processes. The subject started with the spiral galaxies that Seyfert discovered in 1943. Their bright blue nuclei and broad emission lines implied gas moving too fast to be explained by the normal rotation pattern of a galaxy. In hindsight, it's clear that Seyfert galaxies are the missing link between normal galaxies and quasars, because they have non-thermal emission but are closer and less luminous than quasars. However, since Seyferts have been forgotten for several decades, quasars seemed unprecedented when they were discovered. Using the Hubble Space Telescope, astronomers made deep images and showed that the fuzz around quasars was actually the light of a distant galaxy. In a manner reminiscent of the analogy of Los Angeles at night, this demonstrated that the quasar light source really did live in a city of stars. City of stars. I request an introduction to TeachAstronomy. Just like a hi, what we are. We do have a Discord server. I need to put that in the chat. Let me do that right now. I'm sorry, this is like in the middle of a section, but I always forget to put a link to the Discord server, and I need to do it also on the about page. But for some reason the widget wasn't working a few times, and I need to fix that. But we do have a server. Where is the link to the server? Copy. Okay, let's see if this works for you guys. That's our Discord server. It is called Astropedia. I know it is not the same name as TeachAstronomy, which is very frustrating. I don't know why. We've had this Discord for a long time, and we have done a lot of different projects for things, so it's we've got a lot of different names for stuff, but it's all TeachAstronomy. It's all Professor Impey's group. But yeah, feel free to jump on there. We've got a bunch of different stuff going on. A lot of people talking about astronomy stuff, and we've got a section for the Twitch streams as well. As far as an introduction to TeachAstronomy, we are a group of now like 4-5-ish individuals. 5-ish I say because someone that we're working with is like he helps us out, but he's like in between stuff right now, so he's like working on other things, but he helps us manage our servers. But it's like 5 of us who are led by Professor Chris Impey at the University of Arizona. We are not technically affiliated with the University of Arizona, but Professor Impey is. And we have a few different groups and a lot of different projects that we do. One of the main ones, and what a lot of people from the Discord and this from the beginning of this channel will probably know, is Professor Impey has Coursera and Udemy courses, and also free to watch on those and on YouTube, courses about astronomy and astrophysics, and they're all like the video lecture kind of courses that are free to the public. And Chris's whole mission is to educate the public about astronomy and have a good time doing it. And so that's part of that. We also have a couple different YouTube channels. So Astronomy State of the Art is where Professor Impey does his Q&A live streams, where he will answer literally any question you can think of about astronomy if you ask it. And then we have Active Galactic, which was his student-based group. Do we do deep dives on various topics in astronomy? We do. We actually, oh, that's fun. That's a smart, I like that. I'm gonna do that. I'll put that in our Twitch channel point thing. But yeah, we do some deep dives, on Twitch, less so far. I mean, we have our regular, like, deep dives into specific things in, amateur astronomy on Fridays. Was there a Q&A session today? It's very possible. I was not there for that one, if it was today, but that's very possible. Let me look. But yeah, we do some deep dives. We talked a couple weeks ago about exoplanets, specifically in exoplanet research, because we had an expert who used to be part of the Active Galactic channel come back and talk to us, because he does exoplanet research. So things like that. So if you suggest stuff, we can totally do that. I would love to do deep dives on Wednesdays. And I'll make a way to do those suggestion things. That's a good idea. And also on our YouTube channel, Active Galactic is all deep dive, 5 to 10 minute long videos about specific things or specific telescopes, stuff like that. I don't think there was one this morning. I think there's going to be one later this week, actually. The Q&A session. According to this, it's going to be on the 2nd, which is Wednesday, at noon. Great. So you guys can go and watch the live astronomy Q&A with Professor Impey, and then you can come hang out with me and Michael while we talk about the news. Astronomy news. Only astronomy news. I don't want to talk about the other news. It's never happy. But, a live telescope stream. Actually, the last, not this past Friday, but the Friday before that, we did a live view of a solar telescope viewing. So that was really fun. My coworker Matthew, well, my boss, I guess, my supervisor Matthew, he had a whole setup at his house in Arizona, and we got to see the sun. So yeah, we're definitely gonna eventually try to do some sort of nighttime telescope viewing thing too. But yeah. All right, I'm going to continue with this because that was a long tangent. But that's what TeachAstronomy is. A lot of different things. Okay, so there was a similar attempt to classify the different species of radio sources. Radio galaxies with low luminosity had cores and twin jets that typically ended within the galaxy in irregular lobes of emission. Radio galaxies with high luminosity had cores and one-sided jets, extending to lobes far beyond the host galaxy. The radio sources with the strongest cores were quasars, with rapidly variable radio and optical brightness and extremely high energy densities. The most extreme species of all were called blazars. As suggested by the moniker, they have dramatic brightness variations, sometimes changing from minute to minute. Their properties are consistent with situations where we're looking down the throat of a relativistic jet toward the central engine, the supermassive black hole. Several decades ago, I was in Russia to hunt blazars, but got more than I bargained for. Sometimes the trip seemed straight out of a spy novel. My misgivings started when a pair of heavily built men got into the backseat of the car on either side of me, toting guns. The life of an observational astronomer isn't usually so eventful. We were heading across the border to an ice cream factory in Georgia to barter for dry ice to cool the instrument we brought from the U.S. We'd come to the Russian 6-meter telescope, the world's largest, to study the rarest beast in the extragalactic zoo. The light from a blazar can vary by 100 times the luminosity of an entire galaxy in less than an hour. Our instrument was a photometer that could measure the brightness of a distant source of radiation in less than a second. We were hoping for an unobstructed view into the maelstrom near a supermassive black hole. My partner in crime was Santiago Tapia, a Chilean astronomer whom I met in Arizona. Our hosts were the staff at the observatory, senior PhD scientists paid less than $100 a month, who struggled to buy clothes and feed their families. As a young postdoc working in America, I was rich by comparison. This was Russia in the waning days of the Soviet Union. Signs of stress and decay were everywhere. In Leningrad, we'd seen empty shelves in the markets and long lines for the few restaurants. On the 3-day journey to the Caucasus, where the telescope was located, soldiers stormed the train brandishing Kalashnikov. Lots of Russian words. Soldiers stormed the train brandishing Kalashnikovs to look for bands of thieves. Naively, I went for a hike high above a river valley the day after we arrived. That evening, as we ate watery borscht and dense bread with our hosts, they said I should be careful because Georgian gun runners use the valleys, and they could be unpredictable. We gathered data the hard way. Santiago and I took turns riding the prime focus cage, a metal cylinder at the top of the telescope where the light came to a focus after bouncing off the primary mirror. The cage also housed the photometer we'd brought with us from the United States. The cage had no padding, and despite my layers of winter clothes, I was chilled to the bone by the end of a long February night. But there were moments of exhilaration. One clear night, our target flickered into action, and the instrument's photon counter saw its light surging and falling. I imagined a star being torn asunder as it hit the accretion disk and became fuel for the beast. At the end of the night, we sat with our Russian hosts and ate poor man's caviar, made of finely diced pickled vegetables. We finished a bottle of rough-edged vodka and told stories until a swollen red sun rose over the Caucasus. The elephant problem for active galaxies is caused by selective vision. If you look with radio methods, you'll see a core and jets and lobes, but the majority of active galaxies are radio quiet. If you look with optical methods, you'll see broad emission lines and a bright core with a faint surrounding host galaxy, but miss the jet phenomenon. These two slivers of the electromagnetic spectrum can't tell the whole story. We need other ways of looking. As we've seen, X-ray astronomy led to the discovery of the prototypical black hole Cygnus X1 in 1964. 6 years later, a rocket detected X-rays from two nearby active galaxies, Centaurus A and M87, and a quasar, 3C273. In the 1970s, the orbiting Einstein Observatory had the sensitivity to detect large numbers of quasars. Their X-rays were variable, showing that they came from near the central engine. The ultraviolet and X-ray emission of many quasars looked like thermal radiation from gas at a temperature of 100,000 Kelvin. Excitingly, it matched the models of an accretion disk around a supermassive black hole. Each time astronomers opened up a new wavelength window, active galaxies were detected. The infrared astronomical satellite, launched in 1977, found that quasars were strong infrared emitters. The hunch was that short wavelength radiation created near the nucleus was reprocessed by dust grains farther out into the longer wavelength infrared radiation. During the 1990s, NASA's Compton Gamma Ray Observatory added a high-energy window onto active galaxies. The twin jets that emerge from the poles of a black hole can crank out a large amount of gamma rays. Certain active galaxies have been observed over an incredible factor of 100 million trillion, so 10 to the 20th, in wavelength, from meter length to smaller than an atomic nucleus. In 2018, a spectacular new window onto active galaxies was opened up when a neutrino was detected from a blazar 4 billion light-years away. Until then, neutrinos had only been detected from the Sun and a relatively nearby supernova. The neutrino was created near the Blazars' central supermassive black hole and detected 4 billion years later by an array buried in the Antarctic ice. The elephant problem can be exacerbated by wavelength chauvinism. Astronomers specialize not only in the objects of their attention, but also in their methods of getting tongue-tied. The elephant problem can be exacerbated by wavelength chauvinism. Astronomers specialize not only in the objects of their attention, but also in their methods of observation. Optical astronomers, still the majority of all professionals, are following the classic trajectory of a subject, from naked eye to photographs to CCDs. Radio astronomers often come from an engineering background, and infrared and X-ray astronomers often come from a physics background. Beyond the technical distinctions, there's a tribal aspect to astronomers working at different wavelengths. Sometimes they don't talk to one another when they should. That's the end of that section. Gonna drink some water. How about talking about the lunar descent? Yeah. Yeah, that's the Chinese lunar descent, right? You're talking about? Did they just land? No. Yeah. Chang'e 5 is poised for historic moon landing to collect lunar samples. Yeah, there it is. Yeah. Oh, Caucasus. Is that how you say it? Caucasus. Yeah. The word I was struggling with in Russian. Also, JAXA's asteroid sample mission. I need to write these down. I'm going to write these down really quick. Chinese lander. And JAXA's asteroid sample. Yeah. Very cool. And then the lunar eclipse was mentioned before. And that article. Sweet. I have so many things to talk about. So exciting. Okay. And we are almost finished with this chapter, which is good, because I've got to get going pretty quick. So we will finish this up, and I will leave you with some last notes. So, a matter of perspective. Astronomers attempt to unify the various species in the Zoo of Active Galaxies by supposing that their appearance depends on orientation. Spiral galaxies are flattened, and accretion disks are thin, so it would be expected that the properties of active galaxies would depend on their orientation in space. To use a simple analogy, a sphere always has a circular shape regardless of orientation, while a thin disk might look like a circle, an ellipse, or even a line, depending on how it is oriented. Radio astronomers realize that the difference in radio brightness among quasars might not be due to intrinsic differences in luminosity. If jets accelerating particles to nearly the speed of light were oriented close to the line of sight, their emission would be dramatically boosted. A direct view down the polar axis of the supermassive black hole would show a strong radio core, a one-sided jet, and perhaps a weak halo of extended radio emission. These are the rapidly variable blazars, which make up a small fraction of the overall population, since that orientation is very particular. A side-on view of that same source shows a weak core, twin jets, and extended lobes on either side. I worked on blazars for my PhD thesis and for a decade after. They had the attraction of a sports car to a young man, fast and finicky and just as liable to leave you stranded on the road as to give you a thrilling ride. Blazars are unpredictable because their emission depends on changeable astrophysics close to the supermassive black hole. Sometimes I went to the telescope and almost all of my favorite targets were biding their time, and some were too faint to observe at all. But when I got lucky, Blazars gave me a Guinness Book of Records payoff. At different times, I bagged active galaxies with the highest luminosity, the most rapid variations, the most compact emissions, and the highest polarization. Polarization occurs when the vibrations associated with the electromagnetic radiation are in a single plane. The polarization of light gives information on the geometry of the light source. Good science, however, requires an analytic approach and systematic observations. So my research advanced by the totality of the data rather than by the most exciting moments. I learned that blazars represent a very privileged view onto the central engine. Hot gas moving at 99% of the speed of light means that blazars are hundreds of times brighter than an active galaxy when one is not looking along the jet. Accelerating gas to this speed was a theoretical challenge, but observers like me enjoy taxing theorists. It was eventually possible to identify the much more abundant active galaxies whose behavior was less exciting, representing the view when we're not looking down the jet. My goal was not to claim blazars as unique and exotic beasts, but to give them a natural place within the Zoo of Active Galaxies. These ideas came together in a unified model of active galactic nuclei, or AGN. It's like active galactic videos on YouTube, AGV. Well, we're just AG now, active galactic. The central idea is that all active galaxies are powered by accretion onto a supermassive black hole, and that the observed differences are caused mostly, but not totally, by orientation. Oh, and we have a figure. Let me show you that. That's not the figure. This is the figure. So this says, in the unified model of active galactic nuclei, the zoo of AGN can be thought of as variations on a basic theme. The power comes from accretion onto a central supermassive black hole, but what observers see depends on their orientation with respect to the inner accretion disk, a larger, dusty torus, and the twin relativistic jets. The names of the zoo animals we observe are shown around the edges. Types of AGN, like Seyfert galaxies, radio galaxies, and blazars, are fundamentally the same. This model explains many, but not all of the differences between active galaxies. Cool stuff. Okay, so the central idea is that all active galaxies are powered by accretion onto a supermassive black hole, and that the observed differences are caused mostly, but not totally, by orientation. Oh, I read that already, sorry. Observed properties are strongly affected by obscuration and by the fact that gas in jets is moving close to the speed of light. The intrinsic properties of the nucleus depend on the type of host galaxy, the spin of the black hole, and its accretion rate. Regardless of how differently it presents itself, the elephant is one beast. And that's the end of the chapter. Next chapter for next time will be gravitational engines. Very fun, very exciting. I see Virtual Assistant said, what makes Chang'e 5 robotic? Oh, I don't know. I mean, you know what? I will table that discussion until next time because I am running a little late. And I'm going to have to hop off here pretty quick. But thank you guys all so much for joining me for Chapter 3. Again, like I said in the beginning, I am putting all of the previous chapters onto our YouTube channel, which is also Teach Astronomy. We have a few, but this will be on Teach Astronomy. And I'll probably get those up by the end of the night. And the other channels were, so we have Teach Astronomy, that's where I'll put these, and that's where the courses are. Then there's Astronomy State of the Art, which is where Professor Impey does live sessions, but we're slowly moving him over to Twitch with those. And then Active Galactic is the one that has like short videos, kind of almost like sci-showy. We like to model it off a SciShow and like Veritasium, stuff like that. So, oh no, you're fine for the caps. I'm glad you found us. I'm glad you were excited about it. So excited to find new people. Yeah, so if you're new, feel free to give us a follow so you'll know when we go live next time. And we are also Twitch affiliates, so if anyone is interested in subscribing, that would be super. Oh, I will put those links, yes. But if anyone is interested in subscribing, it is a huge help to the channel. Right now we're all doing this, you know, for fun, because we used to be, oh no, my desktop audio is off. Okay, I was like, I don't know if you guys just heard Professor Impey just start talking. So that's the live sessions is there. Where's the carrot? It's probably not called a carrot, but I put it there. So that's the live session 1. Sorry, I'm like thinking about different things and doing different things and confused. Oh, that's why our Discord is called Astropedia, because technically this is TeachAstronomy. It was named Astropedia first, I guess. The more you know. And then Active Galactic, which I made a lot of videos for and still make videos for, is here. So those are the links to our other channels. There's many. But yeah, feel free to go check those out. Give us a subscribe there. And yeah, like I was trying to say before, we're affiliates. If you want to throw us a subscribe, if you enjoy our content, it would mean a lot. We used to be funded by a grant. The grant has since ended. So yeah, we just want to keep bringing you guys good content. There will be some benefits for subscribers. We're actually planning some stuff. We're going to be talking this week with Professor Impey and stuff about doing a bonus subscriber-only chat stream coming up soon. So just a special thing. But we are not sure what that's going to be yet. So I will get back to you on that. But yeah, I think that's it. Like I said before, Wednesday we have our astronomy news. Wednesday is also going to be a Professor Impey stream on that Astronomy State of the Art, that first link. It will be there. And we'll have Amateur Astronomy Day on Friday. Thank you so much for that subscribe. Oh my god. Thank you so much. I really appreciate it. Yeah, you guys are awesome. I'm so glad I get to do this. This is amazing. So thank you, Intro Fortis. I'm so glad you're enjoying this channel. Enjoy your emote, and I promise more things will be coming soon. That for subscriber benefits. All right, and I guess I will see you guys next time. So have a good rest of your day, and I'll see you on Wednesday. Bye.